So once you've learned about mass spec and IR spectroscopy and C13 spectroscopy and proton NMR, then you're ready to tackle some serious structure elucidation where we kind of bring it all together. So we have a whole problem set, really of problems just like this, where you're given a suite of spectroscopic data, and from that, you get to figure out what the actual structure that is consistent with that data might be. So I'm going to show you my approach to this. So if you look at this, we have a proton NMR on the top, we've got a C13 NMR below that, we've got some IR peaks that were pulled from an IR spectrum, and then we have some high-res mass spec data giving us a very exact, accurate mass. So the high-res mass spec, that mass of 116 point whatever AMU in this case, if you chug that through, you can figure out, or have a computer figure out for you, that corresponds to a formula of C6H12O2. And I'm looking at this first because that is an absolute. That mass corresponds to that formula. And when we know that formula, we can make some good decisions on all of the other forms of spectroscopy. So here, keep that in mind. We've got 6 carbons, 12 hydrogens, and 2 oxygens. Those 2 oxygens mean we could have an ether, we could have an alcohol, we could have carbonyl. Actually, we could have one of each, right? Because we have 2 oxygens. But there are no halogens, no nitrogens, nothing like that. So I start with the most absolute and simplest stuff. And that's, to me, the simplest and most absolute, getting the formula out of that high-res mass spec. Next, I'm going to move up to the IR, because IR is pretty straightforward. You either have a peak or you don't, and those peaks simply tell you what functional group is present or absent if the peak isn't there. So in this case, we have 3 significant IR peaks at 2900, 1740, and 1100 wave numbers. And you've got to know what those mean. 2900 is the sort of generic CH stretching from an sp3 carbon. Most molecules are going to have that, but not all. So we'll just keep that in the back of our head. 1740 wave numbers, that's much more important. 1740 is a carbonyl stretch. So now I know that one of my 6 carbons is involved as a carbonyl, and one of my 2 oxygens is involved in that carbonyl. The other stretch here is at 1100 wave numbers, and that could be really a couple of things. That could be a CO stretch, single bond, or a CN single bond stretch. And this is why we look at the formula first, that formula that we were able to get from the high-res mass spec data, because I know this can't represent a CN single bond, because there's no nitrogen in the formula. So that peak at 1100 wave numbers must be from a CO single bond stretch. Okay, so we know a couple of things from the IR. Next, we'll move up to the C13, because C13 is still fairly simple to interpret. The first thing I'm going to do when I look at a C13 spectrum is count the number of resonances. That's going to tell me how many unique carbon types are in the molecule. And when I look at this, I can see 1, 2, 3, 4, 5, 6. 6 unique carbons because there's 6 resonances. And I know that there are 6 carbons in the formula, and that means that there are no symmetry elements in this structure. All 6 carbons are unique. The next thing I'm going to do is look at what kinds of carbons are present. I'm going to look for interesting carbons, ones that are not in the generic region. And I can see that I have 2. I have 1 carbon showing up a little bit above 170 ppm, and that's at the pretty high range of the pi region. And that is indicative of a carbonyl carbon. And we already know we have a carbonyl, right? The IR told us that we have a carbonyl stretch, so this reinforces it. If your IR tells you you have a carbonyl stretch and you don't see a carbon in that range of the C13 NMR, something's not right. So yeah, that's a carbonyl carbon. The only other carbon in the spectrum that's interesting is this one at about 60 ppm. That's in the electronegative region, and that tells me I have a carbon that is single bonded to an electronegative atom. And because I know the formula, I now know that that carbon is bonded to an oxygen. Again, that reinforces what we learned from the IR. The IR had a peak at 1100 wave numbers, and that was corresponding to what we believe to be a CO single bond stretch. The other 4 carbons are all generic. That really doesn't tell me much. So from the C13, we really didn't learn a whole lot of anything new, except that all 6 carbons are unique, and it reinforced some of the things we learned from the IR. So last, we're going to spend an awful lot of time looking at the proton NMR, because that's really where the main power is. I really would resist the urge to jump directly into the proton NMR. Again, doing all this background stuff first really helps you to start making educated guesses up here with the proton NMR. If you haven't figured out that, oh, this formula only has oxygens and, oh, it has a carbonyl, you're going to be making bad guesses rather than educated guesses. All right, so the first thing I'm going to do here, again, is just count the number of resonances. 1, 2, 3, 4, 5 resonances. And that means I have 5 unique types of hydrogen. The next thing I'm going to do is count all the hydrogens. In other words, I'm going to sum up all of their integrals. Here the integrals are shown as numerical values above each peak. So from left to right, I have 2 hydrogens for that first peak, then 2 more, that's 4, 2 more, that's 6, and then 3 and 3, that's 12. And if I look at the formula has 12 protons in it. And that means that it matches. Remember, the integral values in a proton NMR don't tell you absolute numbers, they technically tell you relative numbers. So if it only had 6 in the actual spectrum, 6 total protons, I would have to double everything to make it match the actual formula. But in this case, it's 12, so it matches. The next thing I'm going to do, similar to what I did with the C13 NMR, is to look for interesting peaks, interesting with respect to the chemical shift. And I only see one. I have one peak at about 4.1 ppm. And recognize that that's not in the pi region, right? That's in the electronegative region. It's very common when you have an NMR spectrum to truncate the spectrum and only show the parts that actually have data. So while a normal proton NMR would range from 0 to 10 or 12 ppm, this one only goes up to 5 because there's nothing above 5. So don't look at it in terms of real estate. Don't think, oh, the leftmost peak is in the pi region. You got to look at the actual chemical shifts, right? The actual frequencies. So yeah, that one peak at about 4.1, that's in the electronegative region. And that means that whatever hydrogens are there are bonded to a carbon that is bonded to something electronegative, which we know is oxygen because we know their formula has only oxygens in it. That's the only electronegative elements we have. So that means we have, in this case, 2 hydrogens because the integral value for those hydrogens is 2. We have 2 hydrogens on a carbon that is bonded to oxygen. All right, so that means we have a CH2 next to an oxygen. But we're still not done with that peak because that peak is a quartet, right? The multiplicity tells us something. The fact that it is a quartet means that n plus 1 is 4, which means that n is 3. This must have 3 identical neighboring protons, and that's usually a methyl group. So if we have a methyl group adjacent to this, can we start putting some things together? Well, let's see what we can do. We know that this was a CH2 next to an oxygen, and we know it's next to an oxygen because of where it shows up. The chemical shift is in that electronegative region, and the only electronegative atoms we have in the formula are oxygens. So I've got CH2O, and you'll notice that I have 2 more bonds kind of sticking out of it, right? That's because that carbon has to go on to a 4th atom, and that oxygen, being divalent, has to go on to a 2nd atom. So that's a really good idea. Just draw little lines when you know there's something else, where it's got to be bonded to something else. And we know what one of those things is. We know that we must have a methyl group attached to that CH2. Because that CH2 resonance is a quartet, right? And so with 3 neighboring hydrogens, n plus 1 is 4, making it a quartet. So look at all the connectivity, look at all the information we got, kind of out of just that one peak. And we only got that far with that one peak because we knew some other things from, in particular, the mass spec data, right? The formula. So I don't have any more interesting peaks with respect to chemical shift. All the remaining hydrogens are just generic hydrogens. So where I start next is with any proton set that integrates for 3 or multiple of 3. And the reason I do that is pretty straightforward. Think about when you're doing a jigsaw puzzle. How do you start a jigsaw puzzle? You start on the corners and the edges, right? And the reason you do that is because the edges and the corners can only go inward. They can't go in like 4 different directions. They can only go in 1 or 2 directions. It's just a lot easier. So it's a problem-solving strategy. And methyl groups are kind of the same thing, right? If you have a CH3, it can only go on to 1 more thing. If you start with something that integrates for 2 protons or 1 proton, those are going to go off in multiple directions, and it just makes things complicated. So in this case, I have 2 peaks that integrate for 3, so likely 2 methyl groups. Now here's the thing. I already know where one of them is. That blue methyl group that I implied to exist next to that CH2 quartet, that orange CH2, I knew that that existed. So as soon as I drew that blue CH3 over there, remember that CH3, that blue CH3 is not actually what that quartet at 4.1 ppm actually represents. We're implying it exists because of the multiplicity, that quartet. Well, if you look, I have two generic CH3 peaks, and they're both triplets. And whatever's next to that orange CH2 will be split into a triplet, right? Two neighbors plus one, and plus one is two, therefore, and plus one is three, excuse me. And that means it'll be a triplet. So one of these two methyl groups here was a blue methyl group, this blue methyl group. So I have to look for that. It has to exist somewhere. But because I already know where it's connected, I know it's connected to this orange CH2, I'm just going to put a big X through it so that I don't accidentally incorporate it twice into the molecule. So the orange CH2, that quartet at 4.1, the multiplicity allowed me to imply the existence of a CH3 that is a triplet. I have two of them, so I'm just going to wipe one of them out. Say, yep, I've dealt with you. I know exactly where you're connected. Now that still leaves me with another CH3. And it's also a triplet, right? It's next to another CH2. Again, because it's a triplet, n plus 1 is 3, therefore n is 2. It must have two neighbors. So I have a CH3, which will look as green, and I know what's beside it. I know it's beside two protons because, it's, again, that peak is a triplet. Now, I only have two more peaks on the actual spectrum, and unfortunately, they both integrate for 2. So which one is beside it? Which one of those two remaining CH2 peaks is actually next door to this green CH3? Believe it or not, we can actually figure this out. If something is beside a CH3, it will be coupled into at least 4 peaks, right? Whatever the CH3 is beside, it will act as a neighbor, and there are 3 of those hydrogens, so n plus 1 is 4. It will split whatever it's next to into at least a quartet. And if you look at those two remaining CH2 peaks, one of them is a triplet, and one of them is a rather complex multiplet. And that tells me that it can't be that triplet. That CH2 triplet has to be beside less than 3 hydrogens. And that means this CH2 in purple, right? Again, I know that's a CH2 because of the integral. That CH2 must be connected to my green CH3 methyl group. And because I've incorporated it into the actual pieces up here, right? I've attached it to this green methyl, right? This green methyl is not the purple, right? The green methyl is the green methyl, it's the CH3, but I can imply this purple exists and then I found it here, so I don't accidentally put it into the structure twice. I'm just going to put a big red X through it down there. And that just leaves me with one last peak, this CH2 triplet. Okay, it's a CH2. And again, I have 2 lines sticking out of that because, well, CH2 needs to bond to 2 more things. Where is that CH2 attached to? Well, it's a triplet. So that means that n plus 1 is 3, n must be 2, so it must have 2 neighboring hydrogens. Now I have 2 other peaks that integrate for 2, right? The orange CH2 and the purple CH2. Now the orange CH2 is kind of landlocked, right? It's already bonded to 4 things: the methyl group, the hydrogens that are a part of it, and of course the oxygen. So it cannot be bonded directly to the gray CH2. The purple CH2, however, which I already know is attached to the green methyl group, that purple CH2 has a hole, right? It's got a piece that it can connect to. And if I connect it to that, if I connect the gray CH2 to that purple CH2, it will turn my gray CH2 into a triplet, which is perfect. So if I do that, and again, I'm going to put a big X through my gray CH2 since I know where it connects now, I now have a propyl group. And look at what that does to the purple CH2. That purple CH2 now is coupled by 2 different sets of protons. The green methyl group, technically into a quartet, and then the gray CH2 next to it, technically into a triplet. So the purple CH2 technically should be a triplet of quartets, 12 peaks. And if you look at the actual purple CH2, we already put a big X through it right here at about 1.7 ppm. I don't know if that's 12 peaks or a lot, but it's a lot of peaks. And remember that Pascal's triangle, we saw that those outer peaks tend to get really small as the inner peaks get bigger, and so the outer peaks can kind of get lost in the noise. So yeah, I'll buy it. I'll say that that's just a complex multiplet, and a lot of the little peaks just got buried somewhere and you can't see them. all right, so that's it. We're out of protons, right? We're out of peaks in the proton NMR. So at that point, I'm just going to stop and I'm going to say, okay, fine. What do I have drawn here? Well, on the far left, I have this ethoxy group, and that is 2 carbons, 5 hydrogens, and 1 oxygen. And then I have this propyl group, which is 3 carbons, 7 hydrogens, and that's it. And if I add all that together, I have 5 carbons up there. But I know my formula has 6 carbons, so I'm missing something. And this is where the rest of the spectra that we looked at comes into play. Because we knew we had a carbonyl, remember? And that's my 6th carbon. So I have a carbonyl. Let me assemble my carbonyl. Okay, so there's my carbonyl. Now that's not a part of my proton NMR, but I know it exists, right? I knew it existed from the IR and from the C13. And so this is where we're going to invoke the Mr. Potato Head rule. What I look for here is my potato. You're familiar with Mr. Potato, probably. Mr. Potato is a potato with a bunch of holes in it, and into those holes you jam ears and noses and eyes and things like that. You don't jam an eye into another eye. You don't jam a nose into a mouth or something like that. You have to put the actual pieces into the holes on the potato. In other words, each one of those pieces, the lips, the eye, whatever, connects to one thing, the potato, but the potato connects to lots of things. So I need to find my potato. And my potato here is the carbonyl, because that carbonyl has 2 things missing, right? That's why I drew the 2 lines sticking out of it. That carbon wants to be bonded to 4 things, and it only is bonded to, well, 2, to the oxygen twice. So the carbonyl in this case is my potato. Now you're not always going to have a potato, but you often will. So now I have my potato, and if you look, I have this ethoxy group here, and I have this propyl group here, and that's like an ear and a nose. So I can just jam one of these into one piece of my carbonyl, like this, and then I can jam the propyl group onto the other side. Of course, it doesn't matter which side is which, because of the symmetry of that carbonyl. And I'm going to exchange my methyl group for one that's pushed the other way. And what I get is something that looks like that. By invoking the Mr. Potato Head rule, it prevents me from, say, mashing the ethoxy group into the propyl group. If I did that, that would be a legitimate molecule, but it would be short the carbonyl. So this is how it's put together, and this is in fact the actual answer. And it's a good idea to always go back and check, make sure the formula is accurate, and it is. This has a formula of C6H12 and 2 oxygens. Yep, that matches. And then go back and check everything else. We see that it has a carbonyl, which we knew from the IR and the C13. It has a carbon-oxygen single bond between the orange carbon and the orange oxygen. And there's no symmetry in the molecule. Remember, we established that from the C13, having 6 unique resonances. And then with the proton NMR, I can see that it has 1, 2, 3, 4, 5 different kinds of hydrogen, all color-coded conveniently. And we saw 5 resonances in the proton NMR. And then I'm just going to start on one end and march forward and make sure all the peaks make sense. So starting from the left, the blue methyl group, I should have a generic, because that would be a very generic set of hydrogens. I should have a generic CH3 coupled to a CH2 into a triplet. And I do, I have it right here, right? Put a big X through it already. Next, I would have the orange CH2, and that will be in the electronegative region because of that carbon being bonded to oxygen. So a peak that integrates for 2 in the electronegative region coupled by this triplet, by this CH3 into a quartet. And that's exactly what I see here. The carbonyl, of course, doesn't have any hydrogens on it, so we don't have to look at that for the proton NMR. The gray CH2, it's generic, and it's next to another purple CH2, splitting the gray CH2 into a triplet. So we should see a CH2 triplet somewhere in the generic region, and right there it is. Next, we have this purple CH2, also generic, and sandwiched in between the gray CH2 and the green CH3. So it's going to be split like crazy, right? Lots of coupling there. So we should see a really complex-looking CH2 in the generic region, and sure enough, we do right here. And then lastly, we have this green CH3, very generic, and next to a CH2, the purple one, that would split it into a triplet. So we should see another generic CH3 triplet, and that's this one right here. So it all matches up. Let's do another example. Again, we're going to start from the absolute most simplest stuff, the stuff that's just not questionable. So in this case, we can see that the high-res mass spec will give us a exact mass of 112.1252, and chugging that through will give us a formula of C8H16. So here we've got 8 carbons, no heteroatoms, so no carbonyls, no ethers, no alcohols, no amines, no alkyl halides. Really just what, maybe a benzene or an alkene or an alkyne or something, or just a plain alkane. Next, looking at the IR, and we have 3 significant peaks here, a peak at 3050, and that is most likely going to be CH stretching from an sp2 carbon. We have a peak at 2900, which is CH stretching from an sp3 carbon, and then a peak at 1620 wave numbers, and that is going to wind up being a stretch from a carbon-carbon double bond. So that tells me I have most likely an alkene or possibly a benzene ring. Remember, benzene is that 6-membered ring with 3 double bonds in it. And I have 8 carbons in my formula, so this could support a benzene ring. I can pull one more piece of information out of this though, right? That peak at 3050 tells me that I have an sp2 carbon bonded to an H. And now I know that that sp2 carbon is likely an alkene or a benzene ring. So my alkene or my benzene must have an H directly attached to one of those carbons. All right, let's look at the C13. First thing I'm going to do is count actual resonances. And in this case, I see 1, 2, 3, 4, 5, 6, 7. There are actually 2 right at 20. They're kind of mushed together, but that's actually 2 resonances. So that's a total of 7 peaks, and I have 8 carbons in my formula. And what that tells me is that I have 2 carbons that are identical. There's some kind of symmetry, either a mirror plane or rotational axis, something like that. So that's useful information. Next, I'm going to look for interesting carbons with respect to chemical shifts. And in this case, I see 2, and they're in the pi region, above 100. And they're in the lower end of the pi region. Again, don't just look at it as, they're far to the left. They're actually in the lower half of the pi region. And those are indicative, again, of either carbons that are in an alkene or a benzene. But now I can see it's an alkene. The molecule has 8 carbons in the formula, but 6 of those carbons are in the generic region, so clearly it can't be a benzene. It would have to have 6, right, or at least 6, but 6 in the electronegative region to actually have that. And it doesn't have enough carbons left over. So this is an alkene, and the remainder of my carbons are all pretty generic. So the C13 helped a little bit. It tells me that I have a little bit of symmetry and that I definitely have an alkene and not a benzene ring. All right, so now we look at the Proton NMR, which is, again, where you're going to spend most of your time. Let's start off by counting the number of resonances. In this case, I have 1, 2, 3, 4, 5, 6 resonances. So 6 unique types of hydrogen. And then I'm going to count up the actual integrals. I'm going to sum those up. Again, starting from the left, I have 1, plus 1 is 2, plus 2 is 4, plus 3 is 7, plus 6 is 13, and plus 3 is 16. And when I look back at my formula, it has 16 hydrogens, so I don't have to double or treble or anything like that. So next I'm going to look for interesting peaks with respect to chemical shift. And again, I only have just the one. I have a peak at about 5.2 ppm. And that is in the pi region, the lower end of the pi region. And remember, when you're looking at a proton NMR, you can subdivide the pi region into 3 separate subranges. From about 5 to 6.5 is where you see true alkene hydrogens. They're called vinyl hydrogens, but a hydrogen really directly attached to the C of a double bond, an alkene. And then from about 6.5 to 8.5, that's where you see hydrogens of a benzene ring. They're called aryl or phenyl hydrogens. And then above that, above about 9, give or take, that's where you start to see aldehyde hydrogens, an H directly bonded to a carbonyl carbon. So in this case, that is a very distinctive alkene hydrogen, a vinyl hydrogen. And there's only one of it. So I can tell that I have 1 hydrogen attached to my actual alkene, which I was actually kind of already aware of because of that CH stretch in my IR, right? We had an sp2 carbon hydrogen stretch. So we knew we had at least 1 hydrogen attached to one of those alkene carbons. All right, so let me go ahead and put together my rather dumb-looking alkene with 1 H on it, okay? And again, notice how I'm putting extra bonds around because I know that that alkene must go on to 4, that's not where it goes though, it must go on to 4 different things, right? Well, 4 things anyway, don't have to be different. So in this case, I know one of those 4 things attached to that alkene is the hydrogen. That's, I know that because that's what that peak at 5.2 is telling me. I have a vinyl hydrogen, right on an alkene. And it integrates for 1, so I know there's only 1 there. So we're not done with that peak because we can see that its multiplicity is a triplet. And that means that it must be beside, most likely, a CH2, right? If it's a triplet, that means n plus 1 is 3, n is 2, two identical neighboring protons. Now, there are a couple ways we could put this together. We could have, perhaps to the left of this CH, a CH2 here, or maybe this carbon here. I mean, it has 2 slots. Maybe we should put 2 hydrogens there. Hopefully you can see that's not the way it's going to work. If I had 2 hydrogens here, for one, they actually wouldn't be equivalent. They'd be diastereotopic because one would be cis to this existing H and one would be trans to it. But more importantly, they would actually be vinyl hydrogens, right? They'd be hydrogens and they would be in the pi region, and we don't have any more hydrogens in the pi region. And that means that this carbon hydrogen, this hydrogen here must be attached to some other CH2. So I'll put it here in blue. And again, my CH2 has to go on to one more thing, so I've got that extra bond there. Now look at all that connection we've got, right? Look at all that connectivity just from that one little wiggle on a spectrum. We got all that put together. Now, admittedly, part of the reason we got that far was by looking at some of the other information below, but that's a lot of stuff we can squeeze out of that one little wiggle. All right, so I'm out of peaks that are interesting with respect to chemical shift. So that means that I'm going to look for peaks that integrate for 3 or multiples of 3, and I've got quite a lot. In this case, I have, let's go to the far right. I have a CH3 triplet, and I say that it's a triplet because it's kind of mushing up against that other peak. So just to make sure it's clear that it's a triplet, I have it drawn out that way. Okay, so we have a CH3 triplet. Okay, there is a CH3. And the fact that it's a triplet tells me it's beside a CH2, right? N plus 1 is 3, so N is 2, 2 neighbors. Do I have a CH2 on my spectrum somewhere? Yep, I sure do. Right here. It's the only one, actually. So now I know that the green methyl group here, represented by this triplet, must be directly attached to this exact CH2 because it's the only CH2 on the entire spectrum. Okay. Well, if that's the only CH2 on the entire spectrum, doesn't it have to be this blue CH2 right here? The one that I implied existed because of the triplet effect, the triplet coupling to this here? Yeah, there's only one CH2 and I already established it here, and that means that this green CH3 is actually attached to that. Okay, so I'm just going to have my little green CH3 here and a big X through it like that. All right, I next have this integrating for 3, this singlet here. Okay, that's not terribly informative, but what is that going to do for me? Let's see, what can that do for me? Well, it's a singlet. It means it's not really beside much of anything. So if it's a singlet, that can be kind of hard to figure out where it goes, right? If it's a singlet, need another color here. If it's a singlet, then how can we actually deal with that? Need a better color here. Well, we don't know where to put it. That's the problem. So I'm just going to let it hang there. Oh, that's a terrible color. Let's try a different color. We don't know what to connect it to, so that's kind of a dead end right now. We do have one more peak that integrates for a multiple of 3, right? This peak here integrates for 6, and it's a doublet. Now, the easiest way to have 6 identical protons, you can't put 6 H's on one carbon, but you can have 2 identical methyl groups. And remember what we learned from our C13 spectrum here, that we had 2 carbons that were identical because it only had 7 resonances in the actual spectrum, but 8 in the formula. So apparently, we now know that those 2 carbons have 3 hydrogens on them. So this doublet here of 6 hydrogens is actually 2 identical methyl groups. And it's a doublet. And because it's a doublet, that means that n plus 1 is 2, n is 1. Well, if n is 1, that means that we need a CH to attach both of these methyl groups to. Now we have 2 CHs in our spectrum. We have this vinyl H, but he's kind of all done, right? I can't put anything else attached to this carbon because he's already got a full octet. But we have this other one that we haven't really dealt with here. And it's complicated looking, right? It's pretty well heavily split. If you were able to blow this up and look at it, it should have 7 peaks, and it actually does. Because that septet would be n plus 1 is 7, so n is 6, it would have 6 neighboring hydrogens. And that's exactly what we see in those 2 gray methyl groups that are identical to one another. So I'm going to move these methyl groups, right, which I know exist. It's 6 hydrogens total, and it's one type, so it's one peak, one resonance, but it's coupled into a doublet because they are both attached to a CH, and the only CH I have really left that I can attach it to is this purple one right here. So now that CH should be a septuplet technically. And that's it. We're out of peaks. So now we invoke the Mr. Potato Head rule. I see I have a methyl group, that's an ear. I see this, what's commonly referred to as an isopropyl group, and that's a nose. But I look at this chunk here that I put together, and it's got 2 holes to fill. So I'm just going to plug in my ear and my nose into those 2 holes. So I'll put my isopropyl group up here, like this. And what else do I have? My methyl group. Oops. This guy right here, which I need to flip around so that I can attach it correctly, like that. There. And that's it. I'm out of peaks, I'm out of pieces. Let's see what we can do. Let's check the formula. I have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and that's exactly what the formula says. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens, and that's what the formula has. And there's nothing else. There are no other heteroatoms. So everything matches up so far. I can see that it has an alkene, and I knew that from the C13 and from the IR. And then I'm just going to march through the entire structure and look at it, comparing it to the Proton NMR. So starting on the far left with this green methyl group, that's very generic, right? It's not bonded to anything electronegative. It's not pi bonded. So those 3 hydrogens will be coupled by the neighboring 2 into a triplet. So I should have a generic looking CH3 triplet. And I do. I put a big X to it right over here. Next, I have a slightly less generic, but still generic CH2. And it will be coupled all to hell because it's going to be coupled by the 3 green hydrogens next door and the orange hydrogen right there. So technically that would be a doublet of quartets. It would be coupled into a doublet by the orange hydrogen, into a quartet by the green hydrogens. So one hydrogen that integrates for an awful lot of stuff and technically would be in the generic region. So I have that right here at 2.0, right? That's really complicated. If you blew that up, I believe that's a doublet of quartets and integrates for 2 and it's in the generic region. Next, we have this orange hydrogen, a vinyl hydrogen as it's known, but it's an alkene hydrogen. So I have 1 hydrogen in the lower end, the sort of alkene region of my pi region. And it's coupled by, well, nothing next door here, but 2 next door here, so it should be a triplet, and that's exactly what I see. This carbon has no hydrogens on it, so we can ignore him. We've got this sort of purple CH3, and it's fairly generic, and it has no neighbors, right? On the adjacent carbon, there are no hydrogens. So n is 0, n plus 1 is 1. I should have a CH3 singlet, and I do right here, and it's generic, right? Below 2. And then I have this sort of weird, what's commonly referred to as an isopropyl group. But if you look at it, I have this sort of purple-ish CH, also fairly generic in terms of where it should show up. It's not next to anything with it, or not attached to a carbon with a pi bond or a bond to an electronegative atom. So a boring CH, and it has 6 identical neighbors, right? These 3 methyl groups here, those hydrogens are the same as these 3 hydrogens. And that means it has 6 total identical neighbors. So n is 6, n plus 1 is 7. I should have a generic CH septet. And I do, that thing right here. If you really blow that up, you can see that this peak at about 2.5 is a septet. And that just leaves the gray methyls. There are 6 total protons, and they are identical, and each one would be coupled by this purple CH into a doublet, right? 1 hydrogen, 1 neighbor, so n is 1, n plus 1 is 2, a doublet. So I should have a 6-proton doublet, again, quite generic, and there it is. So that's just how I like to approach these questions. It really maximizes, I think, your time usage, and it allows you to make good guesses when you're starting to do the more complicated stuff, which is mostly the Proton NMR. So good luck with that.